All right. Well, the mic is back because I found the batteries. So that's good. You know, somebody put some spare battery into the file cabinet drawer, so I found it. So now I get my voice back. Yay. All right. So Roshi, okay, I remember. Yes, I remember. There you go. And for some reason, it doesn't echo as bad now. See, I can stand here and it doesn't do the feedback thing. Okay. Very good. So are there any questions about the homework assignment?
Yeah.
Yes. Well, as the holodeck doctor always say, state the nature of your emergency. And then he rolled his eyes. Yes, go ahead.
No, I was about to ask, have you started recording this?
Yep. That's what it's indicating. Good thing. Good to check that. Yes.
And now, when we're writing G, you said we can just use the definitions like this.
Yes.
And then to do F prime or whatever, or G inverse, we are allowed to define anything else we deem necessary to do that.
Yeah, but you know, if you need to define anything other than making use of the stuff that I have already derived, then you may be doing something a little more than what you need.
Yeah.
Okay, so let me just kind of go back and talk about that a little bit. And it's in, sorry? Go ahead.
Do we need to copy in your definition of f of x, y, and k of I, or can we just assume that?
You can assume.
Fine?
Yep, you can just assume.
Okay.
And let me see, where is that? Oh, more, yes. Okay, there you go. So this is your homework. Let me just kind of read the homework itself a little bit so that you guys understand what you're supposed to do. So in your homework assignment, you have to define a bijective function, f3, so that you have a domain. So from your perspective, your domain is n times n times n. That is your domain, the domain of f3. And you have to map it, you know, using a bijective function to just n itself. So that means, okay, if you spell it out, the domain of f3 is n times n times n. And f3 is a function that maps this domain to this particular codomain. So this is a 3D space, you know, of natural numbers. This is a 1D, basically, line of natural numbers. So you have to define an f3 that is bijective that can do this. Okay? But you are allowed to use the definitions that we have gone through already in class. So you can use definitions already in place in the reading material, which is the one link before the homework assignment. So let me go back to the reading material right before the homework assignment. Okay, I'll open up in a new tab, so this way we can refer to the homework and also the reading material side by side if you need to. So in this case, I have a 2D natural number coordinate system, and I can map it into n. So that's the job of f itself, which of course, you know, you can say f is supposed to be f2 because it maps a two-dimensional natural number space into a natural number line. Is that okay? Are there any questions? Is that okay? All right. So I went through all the gyrations to figure out what is a way. Okay, this may not be the only way, but this is one way to map a n by n domain into an n codomain. And I used the diagonal way to fill in the numbers. And because of the way I fill in the numbers using the diagonal line, I worked out the math and eventually be able to define f of xy is basically x plus y in parentheses and then x plus y in plus 1 in parentheses, the whole thing divided by 2 plus y. Okay? So that's what we talked about last time, okay, on last Thursday. So this is done already. If you need to use something like this, you just refer to f because it is already defined. Okay? Yep.
How is that function injective?
How is it injective?
Yes.
Okay, so injective means every two, if you have two different elements, they will always map to two different values in the codomain.
Oh, so that's why there's no variable in the denominator?
I'm not sure I understand your question.
So it wouldn't be like two of the same answer.
Okay, what is the domain of f? The domain of f itself is n by n, right? It's a Cartesian product of natural numbers. Okay. So what does it mean if f itself is not injective?
And that means we're not using all the elements.
No.
Don't map to unique outputs or codomains.
Correct. So that means if you use the method that I talked about in class and you fill in the numbers, remember 0, 1, 2, 3, 4, 5, and so on. If f is not injective, it means two cells can end up with the same number. Okay? So intuitively, we know this cannot be the case because we are filling in diagonal lines and we are moving out like that, and we don't reuse numbers. There's no way that the numbers can be reused in this case. Okay? But it's not a formal proof. I'm just going to give you the claim that f itself is already injective and it is also surjective. What does it mean if I say f is not surjective? Using this analogy, using the visual way, how would you say that? What do you say when f is not surjective? Say again?
You're not using everything in the codomain?
If I'm not using everything in the codomain is the natural numbers. So that means some natural numbers do not have a matched coordinate in the 2D space, right?
Yeah.
But if I fill in the numbers this way, you can see that intuitively it makes sense that every single number is going to be used. So if you give me any natural number, I can find the inverse and say, yes, something is corresponding to that number in the codomain. Yep.
Can you map out the first 10 real numbers in the 3D coordinate line?
The first 10.
The first 10 real numbers? Because I'm not sure.
Okay, tell me which are the first 10 real numbers.
1, 2, 3, 4, 5, 6, 7, 8.
Those are not, but they're not the first 10 real numbers. There's no such thing as the first 10 real numbers.
Oh, real.
Because you can always find a real number between any two real numbers, right? So there's no way to say the first 10 real numbers. These are natural numbers, okay? So natural numbers, okay. Well, I have to be very picky on these things because with this class, it is all about math, okay? So real numbers are real numbers, natural numbers are natural numbers, and I have to kind of be picky about that. Okay, 6, 7, 8, 9, and here's 10. Huh?
In the XYZ.
In the XYZ one?
Yeah.
Do I want to do that?
Or at least like 3 or 5.
Hmm?
At least like 3 or 5.
3
Be
or
reasonable.
5.
That's be a
He's
bit.
looking like the answers now.
Because once I show you guys, how I come up with the numbers, that basically is the answer. You guys can understand it right away. But you don't even need that. You don't need to see that. Because when you ask me that question, it means that you're not really understanding what f is really doing. Okay? What does f do as a function? What is the domain of f?
And by XYZ.
Okay.
X and Y.
XYZ is not the proper answer because the domain is a what? Is a set. Okay, XYZ is not a set. XYZ are the arguments, they're the parameters, right? Okay, so when we talk about the domain as a set, what is the domain of f? The one that I have defined. It's
Cartesian
n times n,
product.
or the Cartesian product of natural number and natural numbers. Right? In other words, when you look at f, it maps n, Cartesian product n, to n. Give me an example of what is in the domain.
3, 5, 0, 0.
0, 0. Okay, very good. What else?
8, 7.
8, 7. Okay. And so on. Okay, so each element in the domain is a two tuple where the first number comes from the natural numbers, the second number also comes from the natural numbers. So that's basically what we're dealing with. This is the domain of f. Okay, what is f3? f3 is a function. It maps n by n to n. So what is an element? Give me an example of an element.
0, 0,
0, 0, 0. Very good. Okay. That sounds like the name of a movie. Or it's Toro, I think. Okay, another one. 0, 1, 0. Okay, very good. I used the wrong notation. 0, 1, 0. Okay? And so on. Very good. So now that we have an idea what is the domain of f and what is the domain of f3, okay? What is a really useful property of f? It is bijective. What does that mean? It's injective and surjective. Okay, so f is injective and surjective, it is bijective. But because it is bijective, we know it has an inverse function, right? Okay, you give me any natural number, I can reverse that back to a two-dimensional coordinate. Is that okay? So we have a way to fold 2D space into one, and we have a way to look at a one-dimensional number and basically put it back into a 2D space. Is that okay? So now we have a 3D space, right? 1, 2, 3. How can we leverage as much as possible out of f? In fact, I probably will change my homework assignment and say that you have to use f as to express the solution. I think that will force you to think in the right direction, which is not what I really want to do, because I want to give you guys the freedom to think any way you want. Yep.
F of x, y, close paren, z, close paren.
Something like that. Yep. Okay, that's it. I hope the recorder did not actually record that, but I'll have to replace it with something else. But that's basically what it is. Okay, if you fold 2D space into one, then you have 2 dimensions left. Then you fold it again. What does it mean when I say folding space? Folding 2-dimensional space into one, right? So you fold, every time you fold, you are reducing the number of dimensions by 1. You fold once, you go from 2 to 1. You fold twice, you go from 3 to 1, and then to 3 to 2, and then to 1. And so on. Is that okay? All right. Yep.
In our answer, it's okay to, so let's say for instance, it's okay to already use like what you already defined, but are you looking for expansion, like mathematically?
No, don't expand anything, because in the expanded form, it's harder for me to read. Okay. So keep it simple. Just refer to f whenever you can.
Okay.
Just refer to f.
Great.
Okay. So no need to expand any equation. I don't want to see squares and this is this thing over that thing, or this is the floor function or the square root, that sort of thing. Just refer to f and f inverse.
Great.
Okay? Okay, there's one thing about the inverse that you have to know about, because the inverse gives you 2 numbers, okay? So let me just scroll to the part that talks about the inverse. So the f inverse is defined as this thing, you give F inverse a number, a single natural number, it will give you a 2-tuple. This is the first part of the 2-tuple. This is the second part of the 2-tuple. In your homework assignment, you may find it necessary to refer to, oh, I need the first component of the inverse here, or I need the second component over there. Okay, how do you do it? You're looking at it on the screen. You just add square bracket to index it. Okay, square bracket 0 refers to the first component, and square bracket 1 refers to the second component.
Oh wow. That was so much. That's how you do it.
But this has been there since last Thursday. This is not new at all. You need to read this stuff. Okay. So when you read, you need to read in a different way. You know, this is basically saying that when you're reading all the words. But in this class, it's not just the words. The symbols are actually very important. So you've got to read and include the symbols and understand what the symbols are really saying. Okay. But just as a proof, I did not make any changes, since before class, a few hours before class last Thursday. Some of you know that I have a target, and you can say, but Tacky went back in time and changed it, and that's why we don't realize there has been something changes. Okay, so is that okay? Because everybody have an idea of how to proceed with this homework assignment? It's a concept thing. It's never really meant to be a tedious, I have to derive, 4 pages of equation, okay? This has never been intended like that. It has always been intended as a concept question, okay? I give you a function, a magic function that can do this already, okay? Don't ask me how it is derived, it is done already, okay? How do you apply that to solve a new problem? That is the intent of the homework assignment. Okay? Are there any questions? Yes?
So for finding the inverse, we do not need to go through the steps that are on the notes?
That is correct. You basically assume that we already have F inverse defined the way it is like here. It's already defined. So you can just refer to F inverse of a natural number.
And how
And then
would
you
we,
can...
how would we have to change that to work in 3 dimensions? Or just
Well, because this can only reverse a single natural number into a 2D coordinate. It doesn't go all the way to a 3D coordinate. It gets you one step closer. Okay, if F is folding 2D space into 1, this one is doing exactly the opposite. It unfolds, one-dimensional space into 2.
Yeah, got that 100%. How do we take the next step to make it work in 3?
You unfold again.
Unfold again.
Yes. But I'm expecting this class to give me several possible answers because there are different ways to fold. Because you have 3D, there are 3 ways to fold it into one space, into a one-dimensional space. Actually, there are 6 ways to do it because order can be important. So, and then your inverse has to match that too. Your inverse cannot just go like, okay, I'll just randomly apply the inverse function until I get 3 numbers back. Okay, it has to exactly match the way you fold it. Okay. Any questions? Why is this important? Okay, we kind of talked about it a little bit, but I just realized something that can be interesting, maybe not very practical, but it can be interesting for sure. Okay. Yep.
Calculating 3D objects.
Okay. What about specifying pixels of a picture? Okay, what is a pixel? A pixel is a picture element. Okay, so it consists of what? A 2D space, okay, a coordinate, and also RGB, and in some cases RGB, I think alpha for A, A for alpha, or gamma. Which one is it? Alpha. Alpha is the transparency. Okay, so now the question is, can I use one single number to indicate a single pixel? Well, we got x, y as the coordinate. We have r, g, b, and alpha for the actual value at that location, right? So it looks like we have 6 dimensions here. Every single pixel is basically a 6 tuple because we have the location x, y, and then we have r, g, b, okay, the red, green, and blue components, and then the alpha component, which is the transparency. But if we can fold 2D space into 1, we can just apply that 5 times and fold this entire thing into one single natural number. So now, when you need to specify a picture, okay, in a raster mode, you can just give someone a whole bunch of numbers. And each number is representing one picture element on the screen. I mean,
That's how you make friends.
Sorry?
That's how you make friends.
That's how you make friends with aliens. you transmit a picture of yourself using this particular way. Yep.
Isn't R, G, B are only 1 byte of...
It doesn't matter. It's a natural number. It doesn't go negative, right?
Yeah.
So natural number, natural number, natural number, natural number. X and Y are usually natural number because when you look at your screen coordinate, there's X and there's 0, 0, which is usually the upper left corner. Okay, so every single one of these numbers is a natural number. And F can take any 2 natural number and fold it into 1. But the most important point is it can reverse the process because it's a bijective function. Yep.
Is it worth the processing time of calculations over the storage that amount of memory you save?
I don't think you'll be actually saving any memory space because it doesn't really compress it in a way, but it does turn all 6 numbers into one single number.
Isn't it?
I don't know why you want to do it, but you can.
Yeah, why do it?
Encryption.
I don't know. I mean, some of you will get famous and become, sci-fi directors and whatnot. You just have to use this in your movie or something.
Because as much as I understand, isn't a picture is an array of pixels?
Yeah.
And can't they just allocate certain?
But what if your picture is sparse and for the most part it's empty? There's nothing there. You see what I mean? Okay, let's say you have a picture of the night sky with stars, okay? And you don't have a really powerful telescope, so you can only really see a few dots in the sky. Well, you only need to specify where the dots are and what the colors are, because for the rest of the entire screen, it is all black. Okay? Any other questions? No questions? Yep.
I know this is review, but why is there allowed to be a K in the final answer for the inverse? Isn't K Y plus
Yeah,
X?
because I just don't want to write this entire thing everywhere.
Okay.
That's it.
Okay.
I just need a notation so that I don't have to copy and paste this whole chunk, everywhere. That's all.
So you're okay with us having K in there? Just like
No. You just need F or F inverse. You don't need K. I went through the trouble to figure out K so that you don't have to. You don't need K. You just need F inversed and the notation, something like this, because you will need to extract individual components of the answer to the inverse of F. Any questions? Yep. Say again? This is the inverse function of F. I is the argument. So I give you a natural number I. How do I get back the two-dimensional coordinate corresponding to I. This is how you do it. This is the x coordinate expressed in I. This is the y coordinate expressed in I. Is that okay?
What's the O bracket part then?
What is the what?
What's the bracket?
The X
Beneath.
element from the
It's the
returning
floor
to.
function.
No, lower.
Oh,
No, the X element from
That.
returning to.
What's the
Yeah.
bracket O mean?
that's a 0.
So X is 0?
It refers to the first component of the tuple, because when you apply f inverse to a natural number, it gives you a 2 tuple. So there are 2 values. So how do you refer to the first value? How do you refer to the second value? You use the indexing operator to specify, hey, I don't need the whole thing, I just need the first number, or I just need the second number. This is to show you that this is index, this is 0 oriented, which means 0 specifies the first component. Okay. Any other questions? Yep.
In that whole page, where's the actual answer then, if you're not allowed to use K?
F and F inverse. And
Can
the
you-
square
can you-
bracket.
Can you show me in the computer?
Okay, your answer is going to use that. Oh, you need that too.
Yeah, but that's not what I asked.
What are you asking?
You asking for the answer?
No.
No, he's not. He is asking for the notation thing, but I just don't.
I'm not asking neither for the answer nor for the notation.
Okay.
You guys just listen. In the page right there, that page that you have open,
Yes.
where it's where you're solving for just 2D space, what is the answer of that solve thing that you solve for? Like, where is it? Because it's not the thing. It's not the thing on the bottom. Cause
This is 1. This is the F inverse in closed form because K is already
K,
defined.
yeah.
And then this is the other direction. So the other direction is here. This is the other one.
Alright, that's all I wanted.
But this yields a function f blah blah blah, and that suggests that this is the closed form of the answer. Okay, any other questions? So we all good with this? Okay, so remember, in your answer to the homework assignment, you only need to use these things, okay? You don't need to refer to K, you don't need to refer to, this over that, square root and crazy stuff like that. I did all the crazy stuff already, so you don't have to. Is that okay? All right? Okay. See, I spare you from all that crazy stuff because we have more stuff to go over now. You will need all that brain juice for this. So we're moving on to propositional logic, okay? I'm hoping some of you read a little bit ahead of me. I'm gonna ignore this message for now. Okay, so first of all, why is this important? I always want to explain the why first, okay? What is the purpose of propositional logic? I think that is the first part. Is why is it important? Well, it's for proving stuff. Okay, it's for proving something is right or proving something is true, as opposed to proving something, as opposed to counter examples that can prove something is not right. Okay, something is false. So why do we need proofs? I think I explained that already with my example of the dissertation. Okay, something looks intuitive, but it's not. Okay, it's intuitively right, but it is actually not true because I can prove it with a counter example. And why is that even important? Because if you use the wrong theorem as a basis and you write a program based on the wrong theorem, then bad things can happen. Okay. Even for game programming, okay? Even when you're doing game programming, you start with the wrong theorem, the wrong assumptions, then the physics of your world is not going to work out in the end. So your end users will end up asking, so how come I walk from this point to that point, directly? Well, maybe the math involved is not entirely correct. Okay, so it is important to prove that a theorem is correct before we just say that okay, now we know it is correct. So I even refer to my own experience with the master's thesis, which did not have the proof and just said something was obvious, and I was able to prove it wrong using counterexamples. Now math itself is abstract, and it can be dry and boring, but math is also the foundation or the tool that we use in science and engineering, including computer-related work. So what it means is if a conclusion is not true, but it is used as if it is true, a program that is written based on that conclusion or assumption is likely to do something that doesn't match reality. But there's one more reason why your proof is so important. Okay, it's not in the notes here. Okay, it has to do with program verification. Remember the holy grail of making sure a program does what it's supposed to? That's one of the reasons. Okay? We want to be able to prove that a particular algorithm, a program, is going to accomplish what it is supposed to do. Yeah.
I know you said in private industry they don't really verify their programs in that way, but do researchers still do that?
They still research. I mean, it's still ongoing. Researchers usually don't give up because something does not have value in industry. I can give you a lot of examples. How many of you have talked to your phone lately and just do the Google search thing or Siri? Okay, do you guys use that feature sometimes at least? Okay, that's computer speech recognition. And when your phone answers you, it's using computer speech synthesis. Okay. It's practical. When you're driving, you don't want to have to kind of operate your phone and key in whatever you're looking for. You just say navigate to and then the place, and hopefully your phone will automatically find the closest point. Like if you go to Costco, you will locate the closest Costco to your current GPS location, and it just gives you the directions. Okay. That stuff, okay, both speech recognition and also speech synthesis, at one point was considered. It's not. It cannot be done. But people kept on it, okay, and eventually it was done. But most of the time, because of computation power, we just did not have the horsepower to do it in the past. But now we do. And I think it's going to be the same thing with program verification. I think at some point there will be sufficient processing power, at least to apply that to critical algorithms. Maybe not the entire operating system, but the critical part, maybe just the kernel, the really core part of the kernel, we can apply that. So I think people are not giving up on that idea at all. We are just waiting for enough resources to implement it. Okay? But that's a good question. It's a very good question. All right. So the next question, now that we understand why a proof is important, the next question is what exactly is a proof? Does anyone want to just talk about this a little bit? Yep, go ahead.
Why is it important?
No, what exactly is a proof?
Formula that shows
Okay. All right, Mickey, go ahead.
A way to validate the theory.
Okay. But how do you do it? What is in a proof that makes that happen? George, and then
A series of logical statements that lead to a conclusion that you're basing off of the hypothesis.
okay, you mentioned several things that are important. A series, okay, which means there are steps. Okay, 1, 2, 3, 4. Okay, logical steps. Okay, you're applying logic. Okay, it's kind of vague, what exactly is logic, but there are rules that we can apply. Okay, there are axioms and rules that we can apply. Yep, go ahead. Okay, very good. Okay, so you guys have already talked about the main point of what is a proof. A proof is only possible when you have a logic system. Okay, which means you have a set of rules. You have a set of rules, they are self-consistent. Okay, they cannot be self-contradictory because that means it's not possible to do anything. So you have to start with a logic system with axioms. An axiom, in this case, is a simple statement that is assumed true. In other words, you do not question why is that the case. It is just assumed that it is true. In mathematics, in arithmetic, you have a lot of axioms. Okay, give me one.
2 plus 2 is 4.
That is not really an axiom. An axiom is kind of like a transformation when you apply the distributive law. Yep.
Yeah, it's pretty much in linear algebra, right?
Okay.
In linear algebra, you have these 10 axioms for in order to prove something. Man, that class sucked, but I remember all that stuff.
Well, this class is not going to be much better. Okay, A times B is B times A. Okay, multiplication is commutation. It's an axiom. Okay. Well, how do you don't prove this, okay? But I can prove it, okay? I can really prove this. See, 3 times 4 is 4 times 3 because they both give me 12. No, that is not a proof. You're giving me one single sample point that is still true with what we think is true. Okay? But how do you guarantee that this is true for all numbers? You don't. It's just an axiom. Okay? So that's what an axiom is. It's a simple statement that is that's assumed true. A logic system also has transformation rules where one statement can be inferred by another statement or inferred by other statements. So given a bunch of statements that are all true already, there are transformations that can say, okay, if these things are all true, so is that. Okay, we can transform, this bunch of stuff that is true into a new formula that also has to be true. Okay, so you end up with more and more stuff that is true, because of the ability to infer. Okay. These terms are all kind of dry and abstract at this point, but they will become a lot more concrete as we go through the notes. So a conclusion is basically a statement that is claimed to be true and it is proven to be true. A proof in this case is a step-by-step sequence. So once again, it is a sequence, which means it is, you have to, one step has to follow another to link the axioms and statements using the transformation rules until the conclusion is reached. So there are several key concepts here. Axiom is a key concept. Statement is kind of a general description, okay? Basically things that we can derive. Transformation rule is also a key concept here because this is what allows us to generate more and more and more statements until one of those statements to be generated using the transformation rules is the conclusion. Then we are done with the proof. Are we still doing okay so far with this? Okay. In a way, a proof is not creating anything new. Okay, it is more like discovering how to get from one point to another point. Okay, let me just kind of put this up here, and you can just kind of have a mental picture. Once I give you the axioms and the transformation rules, the entire statement space is already defined. Okay, now it can be infinitely large. Okay, but it is already defined. Okay? So think about it like this. If I give you, several rules, okay, several axioms and transformation rules, you already span a space, okay, of all the possible statements. I give you several things here, okay, and I say, okay, assume these 3 things are true. I want you to prove that this is true. Well, if this thing is in the space already, then it is just a question of how do you walk within this map until you get to here. Okay. Are there any questions about this concept? So next time, you have to do another proof in your math classes, just kind of think about it this way. Okay? The question is giving you the starting points. But as soon as the starting points are defined, and the rules are stated. The answer is already here. You are really just trying to find a connection, a path to connect from the question itself, what you start off with the conclusion. That is basically what a proof is. Yep, go ahead. Oh, okay. The row sheet? Oh, stretching, okay. Yep.
So you may be getting to this, I didn't really look ahead, but I was thinking of taking linear algebra currently with this class, and a lot of the proofs that we have to do are in the form of if, P, then Q. And it kind of reminds me of like logical implications.
Yep.
So are we going there? Or?
Oh yes, we are definitely going there. But that's not the only thing we're going to talk about. P leads to Q is a direct proof, but you can also do an indirect proof or a proof by contradiction, which is not Q implies not Q, not P. So you can basically say I negate the conclusion. If you can prove the negation of the conclusion, the negation of the conclusion is false, then you can also say that the negation of the proposition also has to be false. So we'll get to all that stuff. All right, so moving on, this is really just the next one is a review of the logical operators, because we have to rely heavily on logical operators for what we are talking about now. So we basically talk about AND. This is AND. And the way I define AND in this case is it is no longer an quote-unquote operator. I kind of look at this as a function. So I define AND as a function. It's mapping a Boolean value Cartesian product with another Boolean value into a Boolean value. In other words, give it two Boolean values, it will give you back a Boolean value. Okay? An operator is just a fancy way to do the same thing. The definition is this part here. Let me see. We can shrink it a little bit like that. Okay, that's good. So what this means is 0, 0, false and false is false. False and true is false. True and false is false. And then true and true is true. In other words, hey, this is really just the same thing as logical AND in C and C++. Yes, absolutely. I just restated it in a slightly different way using the function notation. That's basically it. Okay. So I use this method to also define what is OR. Okay, this is OR. And you can see that OR is defined as 0, false or false is false, false or true is true, and so on. This is negation. Negation does not map the Cartesian product to true false. It is just true false to true false. So not false is true, not true is false. Okay? So nothing has changed. Okay? We have just changed the perspective. Instead of looking at and or not as logical operators, now we just look at those as functions. We now can define a new operator. The new operator is called A implies B, but A implies B is exactly the same thing as not A or B. So in a way, it is just a shorthand. Okay, instead of writing out not A or B, we just say A implies B. If you want to see the actual function definition of implies, then it is a map again. It is a function. It maps the Cartesian product of two Boolean values into one single Boolean value. False implies false is true. False implies true is true. True implies false is the only time when the entire thing is false. And then true implies true is also true. But if you plug in these values into not A or B, you will get exactly the same result. Are there any questions about the definition of imply or implication? No questions? And this is equivalent, okay, or equivalent to. A is equivalent to B, or even only if B, can be defined as A implies B or B implies A. And because of that, we can basically say, false is equivalent to false is true. False is equivalent to true is false. True is equivalent to false is false. And true is equivalent to true is true. Just different ways of looking at the same thing. So are there any questions about the two new operators that we have introduced here, which is imply or implication, and is equivalent to or otherwise known as if and only if? Yep.
We already been seeing these though.
Yeah, we have. Yeah, we just haven't seen it like a function definition, that's all. All right, so with this out of the way, we are moving on to propositional calculus. What does the word calculus mean? Because most people look at this calculus and go like, oh no, this is calculus again. Why is this not in a math class? So what exactly is calculus? This is one type of calculus, but what is more like the actual definition of calculus? It's just a system of, no, we are not dealing with change here. This is the more narrow definition of calculus, but when you look at calculus in general, what does it mean? It's just a mathematical system. That's all. Yep.
So then what's the difference between saying the algebra or something and the calculus or something? Are they both just mathematical systems?
Algebra deals with what you can do to change the form of a formula.
So it's specific to the manipulation of like symbols.
Correct. So whenever you refer to algebra, including linear algebra, abstract algebra, Boolean algebra, and so on and so forth, they consist of a lot of rules to do the transformations. So this can be transformed into that and so on.
So algebra is part of the calculus system.
I suppose so. But in this case, we'll just take it as this is propositional calculus, and it is by itself it's a 4-tuple. Okay, there are 4 things that you have to specify when you want to specify a particular propositional calculus. It's a 4-tuple. So we'll go ahead and explain what those 4 things are. The first one is alpha. This is uppercase alpha. It is not A, even though it's close. Alpha is a set of symbols to be used in the system. So it will include the constants, it will include the variables, and it will also include schematas. Schematas are symbols that can be associated with a well-formed formula. Okay, so there are 2 levels of abstractions here. Okay, constants, the first one is easy. 0 is a constant, 1 is a constant, true is a constant, false is a constant. A variable can be associated with constants. We just don't know which one, okay? But then we can also use variables, constants, and operators to define what we call formula. And schemata has symbols that can be representing an entire formula, not just a constant, but an entire formula itself. We'll see, we'll have examples later on. But there are 2 levels of abstraction here based on the symbols. But these things are all in the alpha set. The omega set are connectives, which are basically operators. Sometimes people use omega n to refer to a subset of omega where those operators have n parameters. Okay? Now whether we want to break it down that far, I don't think we really need to. So basically omega 1 would be the operators that only has 1 operand, okay, or 1 parameter. Give me one example that we have seen already just from the previous slide. Negation, not. Okay, very good. Negation would belong to omega 1. What about omega 2? And or implies is equivalent to, those are all in omega 2. What about omega 3? Well, that's the good oil that you're supposed to have, like in supplement form. Or eat something. That too. Okay, and this is not a typo. It is not supposed to be WTF. It is WFF. Okay, WFF stands for well-formed formula. Okay, well-formed formula simply means it has no syntax error. Okay, everything is played by they all conform to certain rules. Okay, so we'll take a look at what exactly is a WFF, a well-formed formula. Okay, first of all, everything in A or in alpha is a well-formed formula. So any constant, any variable, and any schemata by itself is a well-formed formula. This is the atomic level of WFF. These are the simplest well-formed formula. Is that okay? So from here, how do we make it bigger? How can we make it a bigger and bigger well-formed formulae? The second statement, basically talks about that. For all I that is between 1 and n, omega I is a well-formed formula. No, this is not omega. This is phi. Phi I is a well-formed formula, and omega is in omega n. Implies that if you apply this omega, lowercase omega, to these specific elements, then the result is also a well-formed formula. Okay, what exactly does it mean? It simply means well-formed formulae can nest. Nest. It's hierarchical. In other words, if you give me n well-formed formulae, okay, in the form of phi 1 all the way up to phi n, if each one is well-formed already, and I take these things and turn them into arguments to omega here, which also needs n arguments, then the result of applying omega to these n well-formed formulae would also be considered a well-formed formula. Is that okay? It's just how you build larger and larger and larger formulae. Yep.
Why do you have two symbols for omega? You say for all I within 1 and n, phi is a well-formed formula, and omega is in omega.
I didn't use parentheses, so basically the way you read this is one portion. So basically I'm just saying that all the phi's are well-formed already. And then the second portion is this one here. Is lowercase omega is in omega n, which means omega, lowercase omega, is a connective, or if you will, an operator that requires n arguments. So when you have these two combined, okay, then this thing is also considered a well-formed formula. In other words, we cannot have missing arguments, and you cannot have non-well-formed formula as arguments either. Basically, that's what it's saying. All right, give you several examples. I'm not sure whether I have examples down there. I think I do. Okay, so let's take a look at the examples down here first. So here's an example. Alpha is defined to be like this, okay? Now this is up to you to define, okay? You can define alpha to be different, okay? You can include more letters if you want. So conventionally speaking, 0 is false, 1 is true, because we're dealing with Boolean logic here. The English alphabet, P, Q, R, S, T, U, those are considered variables. And a variable can either be true or false, but it cannot be by itself another well-formed formula. And then the Greek symbols, phi and, what is the other one? Phi, psi, yeah, that's it. Phi and psi in this case, and also rho, and those three, the first three symbols, the Greek symbols, those are the ones that we can use as well-formed formula. So they can represent, each one can represent an entire well-formed formula. Is that okay?
The one next to rho is variable. It's just P or S.
It's rho.
It's rho as well.
Yeah. R-O. You mean?
I mean, phi, psi, rho, and then after rho is.
This is just regular P.
Okay, so it's just a variable.
Yeah.
Okay.
Okay, so in this case, I just used the regular logic system where omega 1 has just one single operator or connective, which is our negation operation. And then omega 2 has the 4 operators or connectives that we have talked about. This is and, this is or, this is implies, this is equivalent to. Okay. So in this case, okay, let's go ahead and I'm not just going to read the whole thing. So let's try to make up, some well-formed formulae. Now remember, a well-formed formula doesn't have to be true. It just has to be syntactically correct. Okay, doesn't have to be true. So I can say 0, false. That's a well-formed formula. I can say P by itself, it is a well-formed formula. Now that this is a well-formed formula, so is this one. If I connect these two using an AND, that is also a well-formed formula. Somebody is going to say, but the result is just 0, it can be simplified. That's not the point. The point is this is a well-formed formula. Is that okay? I can take this whole thing, which is a well-formed formula, to a negation to it. That becomes a well-formed formula as well. Okay? And then we can say or, and then on the other side we have a psi. That's also a well-formed formula. Yep.
What is it not a well-formed formula? Or just unfinished? Okay.
Or, that's not well-formed. I got 3 things, but what connects, 0 and P to Q? It doesn't have a connector. It's not well-formed.
And if you put PQ in parentheses, it's going to be well-formed?
Sorry?
If you put P and Q in parentheses?
No, it is still not well-formed. What is the connective? You need connectives between elements of alpha.
Okay.
Yeah.
Okay.
Yes. Okay. Yeah, go ahead.
So 0 and P or Q would be well-formed?
That will be well-formed, even though there are 2 ways to put parentheses around it, right? So you can put parentheses around this and then do this, or you can put parentheses around that. You just have to specify the order of operation. Yeah.
When we're talking about connective, that's an element of omega 3, so it has 3 arguments. How do we show that? Like we just put it as a list of arguments after as an operator?
The general application is you specify the name of the connective, and then in parentheses you specify the actual arguments. And the fact that we are used to infix notation is a hindrance because it only applies to up to 2. 3 we cannot really do. If you think about it, the ternary operator in C has 2 symbols. The ternary operator in C is a question mark and a colon, but it's not just one symbol. Okay, can someone explain to me why we do not use the prefix notation? In other words, when we want to say something and something, how come we don't say and then we have P, Q here, P and Q expressed this way? Why not? Well, because we are taught to use infix notation really early on. And that's the thing that's what we're used to. Okay? Yep, go ahead.
But the order would matter also, right?
The order would not matter.
Because some operators, the order would matter.
You mean being commutative?
Yeah.
Well, this part doesn't say anything about that. The transformation rules will talk about that. Okay? This is really just saying what symbols can we use, what operators can we use, and how can those things structure and make bigger and bigger things. So that's what we are up to at this point. It's really just saying, okay, what is a well-formed formula? It doesn't say anything about, oh, if you have this well-formed formula, it can transform into that one. So we haven't really talked about the transformation of well-formed formulae from one to another, just not yet. But that's a good question. That's where we're going to get to next.
Yep.
Okay, go ahead and then he's letting you go first.
Okay. I was just going to say, like, so these are all for just the axiom statements, basically.
These are not even axiom. They're basically it's specifying the language. So they're not even saying, okay, what is true and what is not true. It's just saying, okay, how can we group the symbols so that they become, what we call well-formed formulae. And we don't even process anything that is not well-formed. Yep, go ahead.
So when we're talking about like WFF, is like doing it, I'm not sure if that's pre or postfix notation, but the one that's at the top there, with the two arguments following.
Yeah.
Is that WFF as well? Or?
This one? Well, if you want to use a prefix notation, this will be well formed, and most people just want to use the prefix notation. So I'm kind of flexible in using one or the other. Yep.
Would for example, like your 0 and P or Q, if you were to remove all of the parentheses, would that be considered eligible?
Well, that's what the next paragraph talks about. Let me just scroll down a little bit. So if some really formal system also specifies parentheses in omega, so omega includes the use of parentheses. With the infix notation, operator priority can also be confusing, and we are not going for maximum formality here. So we'll just say that the normal way you use parentheses is going to be okay. If you choose to use the prefix notation, then you don't have a problem with what goes first, because it is always clear. There are always parentheses to tell you what goes first. Okay. What time is it? Oh, it's only 35. Okay. All right. So this is a good time to talk about infix, prefix, and postfix. It's not in the notes, but I just want to give you guys here exposed to the concept of different ways of expressing the same thing. Okay. All right. You don't have to write this down. I'm not going to ask you guys to do any one of these transformations. Okay. All right. So I'll give you like P plus Q, the whole thing, times R, and then this whole thing divided by A times B. Okay. It's all using infix notation. Why do we use infix notation? Because this is how we were taught. Okay. How do I change this to use prefix notation? In other words, you specify the operation, and then you say, okay, what are the arguments that we are operating on?
Make a binary tree.
Make a binary tree? Well, yeah, it is kind of a binary tree, but what is the last operation? That has to be the first operator that we specify. The division, okay? So division, what is the numerator of the division? It's the result of a multiplication, and in the multiplication we have addition PQ, comma R, right? So this specifies the numerator. The denominator itself is another multiplication with A and B as the arguments. So that's the prefix notation of the same thing. This is infix, this is prefix. What is missing? Postfix, okay? So what is postfix then? Postfix means you specify the values first, and then you say what to do with the values, okay? Does anyone have a XP calculator that has RPN? RPN stands for Reversed Polish Notation. That is postfix, okay? All right, so with something like this, let's see how we can specify the postfix notation. Okay, we specify P, we specify Q, then we say plus, okay? Then we specify R, then we say multiply, okay? We don't do anything with the product just yet, okay? Then we say A, B, then we say multiply, and then we say divide. That's how you specify exactly the same thing with older HP calculators. It's based on the concept of a stack. You push P, you push Q, and then the plus is going to operate. It will pop both of these items, compute the sum, and then push the sum on the stack. So you basically collapse two items and turn it into one. So basically these three becomes one item on the stack. Then you push the second thing on the stack. Now you have two items to do the multiplication, to do the product. This product is now just sitting on the stack. I'm not doing anything with it just yet. I push A, I push B. Okay, so now we have three items on the stack. The multiply only applies to the previous two items. So these three things becomes one item. Now I have two items on the stack. The first item is the numerator. The second item is the denominator. The division can now just pop both of these, perform the division, and then push the quotient or the result of the division on the stack. That is how postfix works. But why would anyone use postfix? The fact that I can just look at this and come up with this thing here tells you something that maybe it is useful. Why is it useful? Something is, sorry, go ahead.
Assembly.
Assembly.
You're dealing with the stack closely.
If you're, well, all of these require the use of a stack, because even in a prefix notation, you're still pushing, okay? If you have taken cisp440 assembly language programming, then you know that when you call a function, the parameters are pushed on the stack. So you push P, you push Q, you call the function. It returns a value. That in return is pushed on the stack. You push R, then you perform the multiplication, okay? Then you leave this one on the stack and you compute this side. You push A, you push B, you do the multiplication. Now you have two things on the stack again, and then you call division, and it will do the division for you. So we are still operating using the stack, okay? The question is, what do you see as a main difference between the postfix notation as opposed to the previous two? Yep.
Less function calls?
It has the same number of function calls. It doesn't save time. That is not what it is saving.
Parentheses.
Saving parentheses, very good. And space, okay? Because in postfix notation, there's no need to use parentheses. Yep.
We do all done for recursion.
This requires recursive algorithm to parse. This requires recursive algorithm to parse. This does not.
Oh, okay.
Because you are maintaining the stacks manually. So you don't need to use recursive function calls. What the bottom line is, postfix notation is very, very easy for the computer to parse, to understand. This is by far the hardest. Infix notation is really the hardest notation for a computer to understand. Prefix, easier. In postfix, simplest. And that is why, yep, go ahead.
Which languages operate on postfix?
I was just about to talk about that, so you are ahead of me. Very good. In fact, do we have any programming language that makes use of crazy postfix notation? Post, and then the programming language, script, postscript, postscript. What is postscript? What does it do? What do we use it for?
Letters.
Printers. Okay, very good. Printers or raster or whatever rendering devices. Okay, we can just call those rendering devices. But what is it? What is postfix? I mean, a postscript. What is postscript? What does it do? It specifies how to draw something. That's it. Okay. You can specify. This is the XY coordinate. This is the radius. This is the start angle. This is the end angle. This is the width of the line of the arc. Now draw the arc. Okay? And that's how printers work. Because if you have a 1200 by 1200 DPI printer, and it's a network printer going through Wi-Fi, and you have to transmit the pixels like one by one, how many pixels are you transmitting? A lot, right? Because you're talking about 1200 by 1200. You have this many dots per inch. And then let's say you're dealing with a letter size paper, so you have 11 by 85, right? This is the number of pixels that you have to transmit to specify a picture, something to print on a piece of paper. When you print, you hope that nobody in your household is playing video games. Because they will scream and say, my lag time, what happened to my lag time? It's 200, 300, I can't move. I just died. I know this really well because it happens all the time in my house. Okay? So instead, what do you do? Instead of transmitting pixels, what do you do? Or we encode the pixels using that crazy 2D to 1D folding mechanism thing. Now that will still take a lot of time. What do?
Postscript.
We use postscript. We tell the printer how to draw something. So regardless of the actual resolution of your printer, you still send the same instructions. If your printer is 200 by 200, doesn't matter. because the coordinate is not in actual pixel coordinate. It is in some universal units. Okay. How many people have not heard of Postscript before this class? Okay, so fine. Have you guys heard of PDF? Same thing. Guess why? Same company. Adobe. Okay? Both are inventions of Adobe. PDF is a souped up version of Postscript, but it still operates in the same principle. Are we doing okay so far with those concepts? And if you look into a PDF document, it makes use of postfix notations. They still do. Yep.
Can we dive deeper into that? What do you mean, like it uses the Postscript? It like just does the straight. I don't know. When you remember, like, if I was to pull my PDF file from my Calculus 2 book, what is it like? What do you mean when it says Postscripting? Is it basically like just pulling the pages?
Like, you ever looked at a website and you went to view source and you
Well,
had to get the actual HTML?
Yeah.
So
PDF is actually a programming language. You can specify conditional statements, loops, function calls, and stuff like that. It is a full programming language. So let me see if I can find that. This may be difficult to find because when I type in PDF, Google thinks I want to find PDF documents. Okay, so I'll kind of have to be careful with this one. PDF programming.
If you go to computer file, they have like a 5-minute video.
Yep.
Yeah, see, it pops up all the PDFs. There we go. Okay, first of all, the first thing is make my point, right? Okay, this part does make my point, okay, because from here you can look up what is Postscript, and okay, at the core of PDF is an advanced imaging model derived from Postscript, okay? And Postscript itself is a programming language. You can specify loops, you can specify conditional statements, function calls, functions, function calls, and you can do recursive functions too. So that makes PDF basically the same thing, except it is souped up, okay? Look at PDFs as Postscript plus plus.
So is that like two operators?
And yet it is using Postscript or using postfix notation because it's easy for the computer to understand.
It says, unlike Postscript, which is a programming language, PDF is based on a structured binary file format that is optimized for high performance.
Which means it's tokenized. Okay, which part are you reading?
The start where it says, unlike Postscript, like in the middle of the paragraph.
Middle left, yeah.
Yeah, right there.
So unlike Postscript, which is a programming language, PDF is based on a structured binary format that is optimized for high performance in interactive viewing. But basically what that means is it is still the same thing except it's tokenized. So instead of spelling out the words, they use like a binary code for each thing, like a loop is a different binary code and stuff like that. And they don't store numbers like we store numbers. Like the constant 12 is not going to take up 2 bytes, okay? They're going to use the binary representation of 12, into that file. I remember actually decoding PDF and actually being able to see the code behind it. So there is a one-to-one correspondence between the binary code in the PDF file and the instructions that it is representing. Yep. Mm-hmm.
So in your notation that you have right behind you, if we were to assign values to those variables, how would Postscript know that I meant 12 and 3 and not 1 and 23?
Oh, numbers, you mean like, like this is 1, 2, 3, 123 and not 1, 2, and 3?
Right.
You use another key to force it to enter the number. So this is basically stuck together as one single number, and then you have to press the enter key or say push, okay, to push the value on the stack. Or in some cases, if you have delimiters, like a space character, that can also be used to separate constants. So if you have a space after 1, 2, 3, and then you have 34 after that. Then 1, 2, 3, it can no longer continue to parse as a number because of the space. Then it will automatically push this constant on the stack first. Then it will continue to see 3, 4, interpret that as 34. But if you have a multiply after that, this cannot be, the multiplication symbol cannot be a part of 34, so that will automatically push 34 on the stack. And then it will see the asterisk. Then it will basically say, okay, do we have at least 2 items on the stack? Yes, we do. These 2. Then it will perform the multiplication. The product of these 2 numbers will then be pushed on the stack. So we'll first pop these 2 numbers and then push the product of these 2 numbers back on the stack. Is that okay? All right. All right. So you can probably read through this. It specifies the full language. Okay. That makes a pretty good homework assignment, I think. I'll give you a C program and you guys convert it into Postscript. All right. But this is, I do want to expose you guys to Postscript, or Postfix Notation, because it is used, okay? It has a value. Okay, before we leave today, we are running out of time, but these 2 are really important. The iota set are the initial points, okay? What do we start off with? These are the axioms, okay? Those are the axioms. These are things that you don't question. These things are true to begin with, okay? You don't question why they are true. Zeta is basically, they are the transformations. In other words, they are all in this particular form. Give me, if I can see, psi 1, psi 2, and so on, if I see everything here in this particular set, this symbol means infers, okay? It infers psi, no, not, this is psi already, this is phi. So it infers this new form, okay? Now this is really abstract, it's just a symbol, but later on we'll actually see what we can replace these things with to make it make sense. So we just read ahead of me, okay? Because this stuff can be very dry and very abstract if you don't read ahead of time. But if you read ahead of time, then you have some exposure already. When I talk about it in class, hopefully it is not going to be as abstract. So that's part of your homework assignment, is to read ahead of me, okay? Just finish reading this particular slide. That would be